Hi everyone, this is Alex. Today we are talking about tangents and normals at a point on a curve. By end of this lesson, you'll be able to find the equation of both lines for any curve at any point. Let's start with what we already know. Back when we first learned about derivatives, we defined the gradient of curve y equals f of x at a point P as the gradient of tangent to the curve at that point. In other words, the tangent is the straight line that touches the curve at P and runs in the same direction as the curve right there. Its gradient is the derivative at that point. We have a couple of ways to write this. The gradient of the curve, or its tangent, at a point P can be written as dy over dx evaluated at P with that little vertical bar and the point written underneath, or as f prime of x1, y1. Both means exactly the same thing. Take the derivative and plug in the coordinates of the point to get a single numerical value. That number is the gradient of tangent. So the tangent is easy one. We already know how to find its gradient. We've been doing it all chapter. Differentiate, substitute the point, done. Just a quick note on notation. From here on, I will write the gradient of tangent as m parallel. The little parallel sign reminds us that the tangent runs in the same direction as the curve at that point. Now, the second line, the normal, is the line that is perpendicular to the tangent at the same point P. It crosses the curve at a right angle. And here's the question everyone has. What's the gradient of the normal? You may have heard the rule before. The normal gradient is the negative reciprocal of the tangent gradient. If the tangent has gradient m, the normal has gradient negative 1 over m. Most students memorize this and move on. But I don't want you to just memorize it. I want you to see why it's true. So let me show you something with a triangle. Here's a right triangle sitting in the first quadrant. The hypotenuse starts at the origin and goes up to point A, B. So the horizontal run is A and the vertical rise is B. What is the gradient of this hypotenuse? Gradient is rise over run, so it's B over A. Hold on to that. Let's treat this hypotenuse as a tangent direction. Gradient B over A. Now watch what happens. Because the normal is perpendicular to the tangent, that's a 90-degree angle. Let's rotate this entire triangle 90 degrees counterclockwise and see where the hypotenuse points. When you rotate the point 90 degrees counterclockwise about the origin, the point A, B moves to minus B, A. The x and y coordinates swap places, and the new x picks up a negative sign. So our vertex that was at A, B is now sitting at negative B, A. So what's the gradient of the rotated hypotenuse now? Same idea, rise over run. The rise is A, the run is minus B. So the gradient is A over minus B, which is negative A over B. Now look at the two gradients side by side. Before the rotation, B over A. After the rotation, negative A over B. Here's the trick. Look at how the second gradient relates to the first. The fraction flips upside down from B over A to A over B, and it picks up a negative sign. This is exactly what negative reciprocal means. Flip it and negate it. So there's our rule, and now you know why it is true, not just that it's true. Alright, before we jump into examples, let me show you the recipe. Because every single tangent and normal problem in this lesson comes down to the same two ingredients. To find the equation about tangent or normal, you always need exactly two things. Number one, the coordinates, a point that the line passes through, x1, y1. For us, this is almost always the point on the curve where we are drawing the tangent or normal. Number two, the gradient, the slope of the line. And here's where you choose. If you want the tangent, the gradient is m parallel, which comes straight from the derivative. If you want the normal, the gradient is m perpendicular, which is negative reciprocal of the tangent's gradient. Exactly what we proved with that rotating triangle a moment ago. So, a point and a gradient. That's all you ever need. Once you have those two pieces, building the line is mechanical. On the left, you have the point slope form, y minus y1 equals m times x minus x1. And this is the one I want you to reach for. Here's the trick. It takes your two ingredients and drops them straight in. The point x1, y1 goes here, and the gradient m goes there, and you're essentially done. No solving for C, no extra step. You already have a point and a gradient. So why not use the form that's built to take exactly those two things? On the right, you have the form you've probably seen since your early algebra days, y equals mx plus c. You plug in your gradient m and substitute the point to solve for c, and finally write the whole thing out. It works. But notice, it's a two-step process. Find m, then do extra algebra to hunt down c. Two ingredients, a point and a gradient. One efficient form to combine them. That's the whole engine. Now let's put it to work. Let's start with the most basic type. Find the equation of tangent to y equals x cubed minus 2x plus 1 at x equals 1. Remember our recipe? We need two things, the coordinates and the gradient. Let's get them one at a time. Step 1. The coordinates. We are told x equals 1, but the point needs both an x and a y. So plug x equals 1 into the original curve to find the y value. Then y is 1 minus 2 plus 1, that is 0. So our point is 1, 0. That's the ingredient number 1, done. Step 2, the gradient. The gradient of tangent comes from the derivative. So differentiate. dy over dx equals 3x squared minus 2. And this gives us the gradient at any point on the curve. But we want the gradient specifically at our point where x equals 1. So substitute. Gradient parallel is 3 times 1 squared minus 2, which is 1. So the tangent gradient is 1. That's ingredient number 2. Now we have everything, a point 1, 0 and a gradient 1. Step 3. Build a line. Reach for the point slope form, like we talk about y minus y1 equals m times x minus x1. Drop in the point and the gradient directly. Y sub 1 is 0, m is 1, and x sub 1 is 1. So we write y minus 0 equals 1 times x minus 1. Tied it up, we get y equals x minus 1. And that's the equation of tangent. Notice how smooth that was. Find the point, find the gradient, drop both into the point slope form. 3 clean steps, no solving for c. This is the exact routine we will use for every tangent in this lesson. The curve might get fancier, exponentials, logs, trig, but the recipe never changes. Next one, and notice the word changed. This time we want the normal, not the tangent. The recipe is exactly the same with one extra twist at the gradient step. Let's see it. Step 1. The coordinates. Plug x equals 0 into the curve. Y equals 3 to the 0 equals 1. Anything to the power 0 is 1. So our point is 0, 1. Step 2. The gradient. Here's where we use the box method for a to the box. The base is 3, not e, so remember from 5.7, the derivative of a to the box is a to the box times box prime times ln a. The box is 2x, so the box prime is 2, and the base is 3, so we get 3 to the 2x times 2 times ln 3. Now substitute x equals 0 to get the gradient at our point. The gradient parallel equals 3 to the 0 times 2 times ln 3, which is 2 times ln 3. But wait, we don't want the tangent gradient. We want the normal. So take the negative reciprocal, just like we proved with the rotating triangle. Flip it and negate it. And perpendicular is negative 1 over 2 ln 3. That's our gradient for the normal. The last step, build a line, point slope form again. Our point is 0, 1, and our gradient is negative 1 over 2 ln 3. So y minus 1 equals negative 1 over 2 ln 3 times x minus 0. Tidy up, y equals negative 1 over 2 ln 3 x plus 1. And there's the equation of normal. Next one, and this is a great example to show off a trick that makes your life so much easier. Step 1, the coordinates. Plug x equals 2 into the curve. Then y is ln 2 squared times 2 plus 1, which is ln just 12. So our point is 2, ln 12. Ingredient 1, done. Step 2, the gradient. Now here's a trick. Look at what's inside the logarithm, x squared times x plus 1. That's product. And if we differentiate ln of a product directly with the box method, the box prime becomes a product roll mass. So before we touch any differentiation, let's clean it up using log properties. Remember, natural log of product is sum of the logs. So the y splits into ln x squared plus ln x plus 1. And ln x squared, the power comes down in front, becomes 2 ln x. So it becomes 2 ln x plus 1. Watch what just happened. One ugly log product turned into two simple separate log terms. So if we differentiate this, dy over dx equals 2 over x plus 1 over x plus 1. No product rule, no box prime mess. Now substitute x equals 2 to get our gradient at our point. The gradient parallel is 2 over 2 plus 1 over 2 plus 1. That is 1 plus 1/3, which is 4 over 3. Step 3. Build a line, point slope form. Our point is 2, ln 12. Our gradient is 4 over 3. So y minus ln 12 equals 4 over 3 times x minus 2. Expand and tidy. Y equals 4 over 3x minus 8 over 3 plus ln 12. And there's the tangent. Here's a rule to carry with you. Whenever you see a ln of product of quotient, expand it with the log properties before you differentiate. Turn multiplication into addition, division into subtraction, and powers into coefficients out front. It transforms a hard derivative into a couple of easy ones every time. Next one, and this brings back our inverse trig work from 5.9. Notice, it's a normal again, so the negative reciprocal step is coming. Step 1, the coordinates. Plug x equals 1 into the curve. Y equals arctangent 1. Now, think about what arctangent 1 means. It's the angle whose tangent is 1. That angle is pi over 4, or 45 degrees. So our point is 1, pi over 4. Keep it as pi over 4, exact value, no decimals. Step 2, the gradient. Let me bring up the rule for the derivative of arctangent from 5.9. The derivative of arctangent box is box prime over 1 plus box squared. Here the box is just x, and the box prime is 1. That gives us dy over dx is 1 over 1 plus x squared. Now substitute x equals 1 to get the gradient at our point. And parallel is 1 over 1 plus 1, that is 1 over 2. So the tangent gradient is 1 over 2, but we want the normal, so we take the negative reciprocal, which is negative 2. Step 3, build a line, point slope form with our point 1, pi over 4, and our normal gradient minus 2. Y minus pi over 4 is negative 2 times x minus 1. Expand and tidy, y equals negative 2x plus 2 plus pi over 4. Now let's look at a different style of question. In the example so far, we were given a point and I asked for the tangent or the normal there. This time it works the other way around. We are told something about the tangent and we have to find the points ourselves. This is a classic and is worth knowing well because it comes up constantly. Let's read it. Find the coordinates of the points on y equals x cubed minus 3x plus 2, where the tangent is horizontal, and state the equation of each tangent. Before we touch any calculus, let's think about what's actually being asked. The question wants two things, the coordinates of certain points, and the equation of tangent at each of those points. So I'll write step 1, the coordinates. And right now, they're unknown. That's completely fine. Finding them is the whole job. The key phrase here, and I want to underline it as well, is the tangent is horizontal. This is the clue that unlocks everything. Whenever you see the words horizontal tangent, your brain should immediately translate them into one piece of mathematics. A horizontal line has a gradient of 0, and the tangent always has the same gradient as the curve at the point where it touches. So a horizontal tangent means the gradient of the curve is 0. In other words, dy over dx equals 0. That's step 2. Set the derivative equals to 0. So let's differentiate. So dy over dx is 3x squared minus 3. We set that equal to 0. Now solve. First, take out the common factor of 3. That gives 3 times x squared minus 1. And x squared minus 1 is the difference of two squares. So it factorizes into x plus 1 times x minus 1. So x equals plus or minus 1. We've now got the x coordinates of the 2 points, but notice the question asks for coordinates, so we still need the y values. To find each y coordinate, we substitute the x value back into the original equation of the curve, not the derivative. This is where students slip up, so be careful, go back to the curve itself. When x equals 1, y is 1 minus 3 plus 2, which is 0. So our first point is 1, 0. When x equals minus 1, y is negative 1 plus 3 plus 2, that is 4. So our second point is negative 1, 4. Let's make sense of this with a quick sketch. This is a positive cubic, so it rises from the bottom left, climbs to a local maximum, dips down to a local minimum, and then heads off to the top right. And the 2 points we just found are exactly turning points of the curve. The point negative 1, 4 is the local maximum at the top, and 1, 0 is the local minimum at the bottom. That makes complete sense. At the turning point, the curve momentarily flattens out. So the gradient there is 0, which is precisely a horizontal tangent. At the maximum point, the tangent is a horizontal line, just touching the top of the curve. And at the minimum point, another horizontal line just touching the bottom of the curve. Let's label our 2 points clearly, negative 1, 4 at the top, and 1, 0 at the bottom. Now, for the second part of the question, the equations of the tangents. This is the part students sometimes overthink. A horizontal line always has an equation of the form y equals a constant. The tangent at the top passes through a height of 4, so its equation is simply y equals 4. And the tangent at the bottom passes through a height of 0, so its equation is y equals 0, which is just the x-axis. So there's our complete answer. The 2 points where the tangent is horizontal are negative 1, 4 and 1, 0. And the equations of those tangents are y equals 4 and y equals 0. Next one. The tangent to y equals x cubed at the point 1, 1 meets the curve again. Find the coordinates of this second point. Let's picture it first. Here's y equals x cubed, the standard cubic rising up through the origin. And here's the tangent at 1, 1. Notice how, at this point, the line just touches the curve. It has the same direction as the curve there, but doesn't cross it. The line itself, though, continues in both directions, and down here, in this third quadrant, it missed the curve a second time. That's our mystery point, the second intersection. We don't know it yet, so let's mark it with a question mark, and then go and find it. The plan has 2 clean stages. First, find the equation of the tangent line. Second, find where that line missed the curve. Stage 1, the point we are starting from is 1, 1. Now the gradient. Differentiate the curve. dy over dx equals 3x squared. At x equals 1, the gradient of tangent, I will call it m parallel, is 3 times 1 squared, which is 3. Now build a line using point slope form. Y minus y1 equals m times x minus x1. Substituting our point 1, 1 and the gradient 3, we get y minus 1 equals 3 times x minus 1. Expand and tidy that up. The tangent is y equals 3x minus 2. That's our tangent line. And the curve, remember, is y equals x cubed. Stage 2, where do they meet? At any intersection, the line and the curve share the same y value. So we set them equal to each other. X cubed equals 3x minus 2. Bring everything to one side, and we get x cubed minus 3x plus 2 equals 0. The solutions of this equation are the x-coordinates of every point where the line meets a curve. Now here's a clever part, and it will save a lot of work. We already know one of the solutions. The line was built to pass through 1, 1, a point on the curve, so x equals 1 has to satisfy this equation. Quick check. 1 minus 3 plus 2 is indeed 0. Good. But there's something deeper here. Because the line is tangent at x equals 1, not just crossing the curve, but touching it. X equals 1 isn't an ordinary root, it's a repeated root. Tangency means the curve and the line meet there twice over, in a sense. And that tells us the cubic must contain a factor of x minus 1, squared. So we can write x cubed minus 3x plus 2 as x minus 1 all squared times some linear factor. Let's call it ax plus b. The x minus 1 squared accounts for the tangent point. The leftover linear factor is what will hand us the second point. Now we just need a and b, and we can get them quickly by comparing the coefficients on both sides. Compare the leading terms, the x cubed terms. On the left, the coefficient of x cubed is 1. On the right, when you multiply it all out, the highest term is a times x cubed. For the two sides to match, a must equal 1. So our factorization tied this up to x minus 1 squared times x plus b. Now compare the constant terms, the numbers with no x. On the left, constant is plus 2. On the right, the constant comes from minus 1 squared times b, which is just b. So b equals 2. That gives us the full factorization. X minus 1 squared times x plus 2 set equals to 0. The repeated factor gives x equals 1. That's our original tangent point, exactly as expected. And the new factor, x plus 2 equals 0, gives x equals minus 2. That's the one we've been chasing, the second intersection. Last step, the question asks for the coordinates, so we need the y value as well. And we substitute back into the curve y equals x cubed, not the tangent line. When x equals minus 2, y is minus 2 cubed, which is minus 8. So the tangent meets the curve again at the point negative 2, negative 8. This next one steps things up. And it's the kind of question that separates students who really understood tangent from students who only memorized the procedure. Watch carefully for what changes. Let's read it. Find the equations of tangents to y equals x squared that pass it through the external point 1, negative 3. Notice two things straight away. First, the word tangents, plural. We're being told to expect more than one. And second, that word external. That single word is the key of the whole question, and here's why. Here's the parabola y equals x squared. And here's our point, 1, negative 3, sitting below the curve off to the one side. It's not on the curve. In every example up to now, we were handed a point that sat right on the curve, and we simply found the tangent there. This time our point is nowhere near the curve, so we cannot differentiate at this point. It isn't a point of tangency at all. It is just a point that our tangent lines have to pass through. But think about what we can do from out here. From this external point, I can draw a line that reaches up and just touches the curve, a tangent. And here's the thing. There's more than one. I can draw a second tangent from the very same point, touching the curve on the other side. From an external point to a curve, there are two tangents. That's why the question said tangents, plural. Now comes the crucial move. Where do these lines actually touch the curve? We don't know, and that's the whole difficulty of the question. So we don't pretend to know. Instead, we give the point of tangency a name and let the algebra find it for us. And we have to be careful about how we name it. If its x-coordinate is A, then its y-coordinate is B. If I use two separate letters, I have two unknowns to find, and that will force me to set up and solve simultaneous equations later. But the point sits on the curve y equals x squared, so its y-coordinate isn't free. It has to be a squared. One unknown, one equation, much easier. So let's set it up. Step 1, the coordinates of the tangent point are a, a squared. Step 2, the gradient. Differentiate. dy over dx equals 2x. So at our point, the gradient m is 2a. Now, the equation of tangent using point slope form, y minus y1 equals m times x minus x1. Substituting the point a squared and the gradient 2a, we get y minus a squared equals 2a times x minus a. So far, this is the tangent at a general point on the curve. Now, we use the one fact we've been holding back. This tangent has to pass through 1, negative 3. So we substitute x equals 1 and y equals minus 3 into the equation. Minus 3 minus a squared equals 2a times 1 minus a. Expand the right hand side. Minus 3 minus a squared equals 2a minus 2a squared. Now bring everything to one side and tidy up. The a squared terms combine. And we are left with the a squared minus 2a minus 3 equals 0. And that factorizes beautifully. A minus 3 times a plus 1 equals 0. So a equals 3 or a equals minus 1. Two values of a, which is exactly what we expected. 2 points of tangency, two tangents. Each value of a will give us one of the lines. Now we just fit each value of a back into our tangent equation. Y minus a squared equals 2a times x minus a. Let's work the two cases side by side. Take a equals minus 1 first. So y minus 1 squared equals negative 2 times x plus 1. Expand and simplify, and our first tangent is y equals minus 2x minus 1. The gradient is 6, and the point of tangents is 3, 9. So y minus 9 equals 6 times x minus 3. Expand that, our second tangent is y equals 6x minus 9. And there are our two tangents. y equals negative 2x minus 1, and y equals 6x minus 9. Each one touches the curve exactly once, and each one passes through our axonal point 1, negative 3. This is one of the most important techniques in the whole tangents topic. So let's pin the idea down in 3 pieces. First, when the given point is axonal, it's not the point of tangency. Don't differentiate at it, and don't substitute into the curve. Second, here's the move that unlocks everything. Name the unknown point of tangency as a general point on the curve. Here that's a comma a squared, and write the tangent there. Then apply your one extra condition that the line passes through the given point to get an equation in A. Third, the number of solutions for A is the number of tangents. 2 solutions means 2 lines. Solve for A, substitute each value back, and you are done. This next one shifts gears in 2 ways at once. So keep your eye on both. First, we are asked for the normal rather than the tangent, so the perpendicular relationship between their gradients is finally going to do some work for us. And second, take a look at the curve itself. There's no clean way to rearrange this for y as a function of x. Y appears on its own, multiplied by x and squared, all in the same equation. So we'll need implicit differentiation here. Quick sanity check first, because it costs nothing. Is 1, 2 actually on the curve? 1 squared plus 1 times 2 plus 2 squared, which is 7. Good, we are on the curve. Step 1, the coordinates are 1, 2. Step 2, the gradient. Here's the idea behind implicit differentiation. Even though we can't write y as a function of x explicitly, y is still a function of x, secretly, locally around our point. So we differentiate the entire equation term by term with respect to x, and we treat y as that hidden function of x. So we apply d over dx to both sides. D over dx of x squared plus xy plus y squared equals d over dx of 7. Let's take each term slowly. The first term, x squared, gives 2x. I will write that as 2x times dx over dx, keeping the dx over dx visible in purples so the pattern across the line stays clean. The middle term, xy, is a product of 2 things that both depends on x. So the product rule, differentiate x times y, that's dx over dx times y, plus x times the derivative of y, that's x times dy over dx. The last term on the left, y squared, near the box rule. The outer power gives 2y, the inner derivative is dy over dx, so we get 2y times dy over dx. And on the right hand side, the derivative of the constant 7 is just 0. Now, tidy up. Dx over dx is derivative of x with respect to itself, which is just 1. So whenever we wrote dx over dx, it disappears. That collapses our first 2 terms to 2x plus y. And the 2 terms that contains dy over dx, x times dy over dx and 2y times dy over dx, share a common factor. Pull dy over dx out. It leaves x plus 2y inside the bracket. Now solve for dy over dx. Same algebra you use on any equation. Move 2x plus y across. Dy over dx times x plus 2y equals minus 2x minus y. Divide both sides by x plus 2y, and we get dy over dx equals minus 2x minus y all over x plus 2y. And there's our gradient, but notice something important. It depends on both x and y. That's the signature of an implicit derivative. You generally can't get a clean function of x alone. But that's fine, because we have the specific point in mind. Substitute 1, 2. The numerator is minus 2 times 1 minus 2 over 1 plus 2 times 2, which is negative 4 over 5. So the empirical, the gradient of tangent at 1, 2 is minus 4 over 5. But the question doesn't want the tangent, but it wants the normal. And there's where the perpendicular relationship finally pays off. The normal is perpendicular to the tangent, so its gradient is the negative reciprocal of the tangent's gradient. So m perpendicular equals 5 over 4. And our normal passes through the same point as the tangent, 1, 2. Now we got everything we need. Finish with point slope form, exactly as in every other example. Y minus y1 equals m perpendicular times x minus x1. Substitute the point 1, 2 and the gradient 5 over 4, y minus 2 equals 5 over 4 times x minus 1. Expand. Y equals 5 over 4x minus 5 over 4 plus 2. Combining the constant, y is 5 over 4x plus 3 over 4. Now, here's a question with a genuinely new flavor. Read it carefully and notice what it gives us and what it doesn't. It doesn't hand us a point. It doesn't hand us a gradient. It hands us an angle. Let's see it. Find the equation of tangent to y equals ln x that makes an angle of 30 degrees with a positive x-axis. So somewhere on the curve y equals ln x, there's a tangent line that tilts upwards at exactly 30 degrees, and we want its equation. But to get anywhere, we first have to answer a more basic question. What does an angle has to do with? A gradient. I've deliberately parked those two words up in the corner, gradient and tangent theta, and left them apart for now. By the end of this short setup, we are going to connect them, and the connection is the key that unlocks the whole problem. Let's take any straight line, and let theta be the angle it makes with a positive x-axis. Now drop a right-angle triangle underneath it, a horizontal step across, call it A, and a vertical step up, call it B. Two different things live inside this one little triangle. The gradient of the line is rise over run, and that's B over A. And the tangent of the angle theta is opposite over adjacent, which is also B over A. Now look at what's just happened. The gradient is B over A, tangent theta is B over A, so they must be equal. The gradient of a tangent line is exactly the tangent of the angle it makes with the positive x-axis. Gradient equals tangent theta. There's our bridge. It let us turn any angle into a gradient and a gradient back into an angle. Keep this one, it comes up constantly. Now we can attack the actual problem. Our two usual ingredients are still the same, the coordinates of the point and the gradient there. But this time the order flips. Normally we find the point first and the gradient second. Here the angle hands us the gradient straight away, so we take that first. The tangent makes 30 degrees with the x-axis, so its gradient is tangent 30 degrees, which is 1 over root 3. So our gradient, step 2, is already done. What we don't know yet is where on the curve this happens, the coordinates. So that becomes our open question. Let's sketch y equals ln x to keep our bearings. It passes through 1,0, rises as x increases, and gradually flattens out. And somewhere along the curve, there's exactly one point where it's climbing at the gentle gradient of 1 over root 3. There's a tangent line just touching it. We don't know that point yet. So just as in the last few examples, let's give its x-coordinate a name, call it A, and let the algebra find it. So let's express the gradient as a function of x. Differentiate the curve. The derivative of ln x is 1 over x. So at our point, where x equals a, the gradient of the curve is 1 over a. But we already know what the gradient has to be, 1 over root 3. So we set the two equal. 1 over a equals 1 over root 3. And that immediately gives us a equals root 3. There's our x-coordinate. For the y-coordinate, we substitute back into the curve. Y equals ln over root 3. So the point of tangency is root 3, ln root 3. Now we got everything we need, a point and a gradient. So we finish exactly the way we always do with point-slope form. Y minus y1 equals m times x minus x1. Substituting our point root 3, ln root 3 and the gradient of 1 over root 3, we get y minus ln root 3 equals 1 over root 3 times x minus root 3. Now expand. Watch this nice cancellation. 1 over root 3 times root 3 is just 1. So that term becomes minus 1. And the whole thing tidies up to y equals 1 over root 3x minus 1 plus ln root 3. And that's the equation of our tangent. The new idea in this one is worth carrying with you everywhere. The gradient of the line equals the tangent of the angle it makes with the positive x-axis. The gradient equals tangent theta. So anytime a question talks about an angle with the x-axis, your very first move is to convert that angle into a gradient. Alright, this is the one we've been building towards. It pulls together almost everything from this lesson, including that gradient equals tangent theta idea we made in the last example. The curves y equals x cubed and y equals root x intersect at the origin and a second point P. Part A, find the coordinates of P. Part B, the tangent to each curve is drawn at P. Let theta 1 and theta 2 be the angles that these tangents make with the positive x-axis. By writing the acute angle between the tangents as theta 1 minus theta 2, find the exact size of this acute angle without using a calculator. So ultimately, we are after the angle between two curves at the point where they cross. But before any of that, we need the crossing point itself. Let's do part A. The two curves meet wherever they share the same y value, so we set them equal. X cubed equals root x. Now that third is awkward to work with, so let's clear it. Score both sides, and it will be x to the power of 6 equals x. Bring everything to one side. X to the 6 minus x equals 0. Factor out an x. X times in brackets x to the 5th minus 1 equals 0. So either x equals 0, that's the origin, which the equation already told us about, or x to the 5th equals 1, which gives x equals 1. X equals 1 is the new one. For its y coordinate, substitute back into either curve, say y equals x cubed, and we get y equals 1. So the second intersection is P at 1, 1. Part A is done. Now part B, the interesting half. At P, each curve has its own tangent, and each tangent makes some angle with the x-axis. The angle between two curves is simply the difference between those two angles, theta 1 minus theta 2. So let's deal with the curves one at a time. I will keep the cubic function on the left and the root function on the right. Start with y equals x cubed. Differentiate. The derivative is 3x squared. At P, where x equals 1, the gradient, call it m1, is 3. And here's where the previous example pays off. The gradient of the line equals the tangent of the angle it makes with the x-axis. So tangent theta 1 equals 3, which means theta 1 is arctangent of 3, the angle whose tangent is 3. Now the second curve, y equals root x. Its derivative is 1 over 2 root x. At x equals 1, the root 1 is just 1, so the gradient m2 is 1/2. Same step again. Tangent theta 2 equals 1/2. So theta 2 is arctangent of 1/2. Now stop and think for a moment. If you reach it for a calculator right now, you'll find theta 1 is roughly 71.6 degrees and theta 2 roughly 26.6 degrees. Thoroughly ugly numbers. But the question asks for the exact angle with no calculator. It's telling us not to find two angles at all, but to find their difference directly. And there's a perfect tool for exactly that. The acute angle between the tangents is theta equals theta 1 minus theta 2. And we have the compound angle formula for the tangent of a difference. Tangent of theta 1 minus theta 2 equals tangent theta 1 minus tangent theta 2 all over 1 plus tangent theta 1 times tangent theta 2. So tangent theta will be tangent of arctangent 3 minus tangent of arctangent half all over 1 plus tangent of arctangent 3 times tangent of arctangent half. Now watch the cancellation because it's lovely. We need tangent of theta 1, but theta 1 was defined as arctangent 3. So tangent of arctangent 3 is just 3. In the same way, tangent of arctangent half is just half. The tangent and arctangent undo each other perfectly. So we never actually needed the angles themselves, only their tangents, which are just our two gradients. Substitute them in, tangent theta equals 3 minus 1/2 over 1 plus 3 times 1/2. To clear the fractions, multiply the top and the bottom by 2. Then tangent theta becomes 6 minus 1 over 2 plus 3, which is just 5 over 5, that is 1. And the angle whose tangent is 1 is arctan of 1, which is exactly pi over 4. So the acute angle between the two curves at P is exactly pi over 4. That's 45 degrees. And we found it with no calculator at all. And that brings us to the end of tangents and normals. 10 questions, and on the surface they looked very different. Horizontal tangents, a tangent meeting a curve again, tangent from an outside point, normals to some awkward curves, angles with the axis, even the angle between two curves. But step back, And every one of them came down to the same two things: find a point and find a gradient. Once you got those, you build a line with a point slope form every single time. Thanks for working through it with me. I'm Alex. I will see you in the next one.